Hi all, thank you for tuning into my channel. This is the channel for ozone technology course, and today we will be discussing in session 8A the meaning of particulate matter, sediment, LSI, ozone demand, COD, BOD, TOC, and inorganics. Particulate matter and sediments are similar statements and do have very close meanings. In physics and chemistry, we call both air and liquids as fluids. When we talk of particulate matter, we are discussing the particulate matter in the air, which are actually small particles that float in the air, and these particles are very, very tiny organics like dust, smoke, and all these things are called particulates. They are very serious health risk and may contain toxins. In the air, the particulates are called PM. That's called particulate matter. 2.5 means 2.5 microns in diameter per cubic meter of air, or PM5, that is 5 particles of 5 micron diameter per cubic meter of air, etc. There are regulations as to limit the amount of particulate matter in the air. Sediments, however, are particulates suspended in water or liquid, and sediments are also called suspended solids. They can quite easily be filtered off using sand filters or filter papers, etc. We frequently come across the word LSI, which means is Langmuir Saturation Index. LSI is a theoretical indication of the saturation of the water with calcium hydroxide. Now, calcium hydroxide is the one that causes the hardness. It is soluble in water. So the amount of calcium hydroxide in the water determines how hard the water is. Now, LSC is calculated with using the factors of pH, alkalinity, calcium concentration, total dissolved solids, and the temperature of the water that is to be tested. There is an equation for determination of the LSI, that is equal to the sum of pH TiCiAi minus 12.1, where Ti indicates the temperature, Ci indicates the calcium hardness, Ai indicates TDS, and the saturation index determines the corrosibility of the water with reference to metals. Obviously, calcium hydroxide, the presence of calcium hydroxide actually increases the pH, and therefore the higher the LSI, the less corrosive the water sample is. The lower the LSI, the more corrosive the water sample is. So it is also used as a parameter in the swimming pools, water treatment, boiler feed water treatment, cooling tower water treatment, etc. By determining the LSI, we can calculate how much of acid or alkali is required to balance the water and reduce the corrosion or reduce the scaling. If the SL is positive, the greater the figure, the more the scaling tendency, and if SLI is negative, the water is corrosive and it will start corroding the metals. So you will note that high SLI has a tendency to cause scaling, and low SLI has a tendency to cause corrosion. So we have to balance the LSI to ensure there is no corrosion and there is no scaling. On the right side of the chart, you will find the saturation index. -5 means it is severe corrosion and you have to have the treatment. -3 indicates moderate corrosion, so treatment is recommended. And -2 is moderate corrosion and treatment may be needed. And mild -1 stands for mild corrosion, and we just have to keep watch. Ideally, LSI 0 is the best. Ozone demand is the amount of ozone in milligrams required to completely oxidize both the organic and inorganic materials in 1 liter of water. This factor is used to calculate the concentration of ozone and the amount of ozone to be supplied for the water treatment, which we also have to consider at what rate the water is flowing and how much ozone the ozone equipment is producing. The chemical oxidation, or COD is regularly called, is actually the amount of oxygen required to oxidize all the inorganic materials in 1 liter of water. This factor is used to estimate the concentration of oxygen needed to oxidize the chemicals in the water. The general COD levels are very low in potable water treatment, and there are government regulations specifying COD limits in wastewater. The high COD can interfere with the oxygen supply of aquatic animals. As I did explain to you, COD meaning the oxygen demand, and obviously we can reduce the COD by oxidizing the inorganic materials by ozone. Generally, when we want to find out what the COD is, we send the sample of water to the labs. Therefore, we do not need to know how the COD is measured or determined. However, just for your information's sake, I am just providing you some information as to how they determine the COD. What they do is they take a special weight of the sample, say 100 ml water, or weight of volume and 100 ml of water, weigh it, and then they strongly react with oxidizing chemicals such as potassium dichromate, and then titrate the residual oxidant with ferrous ammonium sulfate. You can obtain the procedure for determination of the COD in the internet. We can also use the COD to determine the quality of the water. If the COD is very, very high, it means there is a tendency for the water to be the chemicals to be absorbing oxygen, and therefore they reduce the supply of oxygen for aquatic animals. BOD is called biological oxygen demand. This is the amount of oxygen required to oxidize the carbon compounds in the water or wastewater. That includes proteins, carbohydrates, and fats that feed and sustain the microorganisms. Generally, the BOD is very low in potable water, and there are federal regulations that set the limit of BOD in wastewater or any other water that is produced from industries. The high BOD suggests a very high organic pollution, and this will also absorb oxygen from the water and reduce the oxygen availability to aquatic animals. Therefore, we had to ensure that whatever wastewater we are providing into the water system, wastewater system, we treat the water to maintain it at a very low BOD. Now, there is two types of BODs. One is BOD3 and BOD5. Generally, we use BOD5. So BOD3 is actually, we allow the water to be digesting for only 3 days before we determine the amount of oxygen in there. Or in the case of BOD5, we allow the fermentation to take place in 5 days. So we determine the amount of oxidation by the organic materials, organic bacteria, by the amount of carbon dioxide produced, and then we extrapolate how much of oxygen is used. There are other methods that can be used to determine the BOD. This slide shows the BOD of the different types of water we find in our systems. Normal water has a BOD between 0 and 3 and is acceptable and is drinkable. The river water has got a BOD between 5 and 20 ppm. This water is polluted, is not drinkable, and requires water treatment. Sewage water has got a BOD between 550 and 100 ppm, and this is polluted and contaminated and unsuitable for drinking without proper treatment. In raw sewage, very high BOD is due to the high fecal matter. And industrial water waste, the high BOD is due to organic waste generally produced after food processing. So industrial water, the BOD can be as between 150 and 1000. This water at this BOD levels are extremely polluted and are not permitted to be drained into the city drainage or sewers without pre-treatment. TOC means total oxidizable carbon. Now, the BOD measures only the carbon compounds that are used up by the bacteria and also absorbing oxygen in fermenting the organic material in the water. For TOC, however, we take an aliquot of the dry sample and treat it with phosphoric acid to remove the inorganic carbon, and then we use an instrument to determine the TOC and TC by drying up the sediments at 105 degrees centigrade and using the analyzer. If you want to know more about TOC and how total TOC is determined, could you please go into the internet and you'll be able to find much more detailed information. The total inorganics can be determined by several methods. The methods commonly used to determine the total inorganics is by evaporating a known volume of water to dryness, heating to ash, and weighing the dried sample. The total inorganics in parts per million will be equal to weight of the ash in milligrams times 1000 divided by the sample volume taken. I have provided you references for determination of BODs, CODs, and total inorganics from the internet, which you can look up yourself. Thank you very much for patiently listening to this session. This is the end of the session 8A. Please go to the next session 8B when it's uploaded, where I will be dealing with VOCs, TDS, conductivity, and half-life. So if this is your first tuning in, please visit sessions 1 and 2, which gives the complete program details, and follow the other sessions 3 to 8A. I would appreciate if you would click the like icon and the subscribe icon so that I will be able to give you notice when I upload the next session. Thank you very much and good day.